Hello, my name is Savan Doshi, and I'm presenting for Group 25 Centennial Campus Building Detection with Ayush Luthra and Malik Thakkar. So, our motivation for this project is that navigating yourself through a new campus can be really difficult. There's lots of different buildings, and if you're on Centennial campus, they can all look the same. Getting familiar with your surroundings takes a lot of time. And a lot of people who are hard of seeing have screen readers, but those screen readers only refer to buildings as buildings, not actually their real names. And that can be tough for students who want to be confident in navigating their own college campus. So, our problem/task is to identify buildings on Centennial campus, specifically EB 1, 2, 3, Fitzwillard, Hunt, and Wolf Ridge. This is because most people take classes on Centennial in these buildings, as well as live in Wolf Ridge apartments. We want to make it available to people who have never seen the buildings before or have difficulty seeing, so that way they can navigate the campus confidently. So, our data. We annotated 584 images. These were taken using drone footage as well as iPhone footage. Each one was scaled to the correct size, and there of EB1, 2, 3, and all the other buildings. Our data had a test and training split of 85-15, and we made sure to take non-iconic images instead of iconic images. The difference between the two is that if you look at the cow picture on your very left, that is an iconic image. It feels like something you'd get off of Google Images as the first result. It only shows the cow. But we need something with noise, like in the real world. So look at the bull on the right. This is more of a non-iconic image. These are annotated using a program called RoboFlow, which allows you to put squares on top of these things and label them. A lot of the data will look like the text file at the bottom. You'll see that first digit 0 is really the object, and then the coordinates xy of the center of the box will be the next two, and then the width and height of that box will be the next two after that. Okay, so for our baseline model, we used Facebook Research's Detectron 2, which is a mask RCNN. The big thing about mask RCNNs is that they use selective search to find out where to find things in the image. So what selective search does is it takes the input image, as you see on your left, and it's able to take very nearby neighbored pixels and combine them together. It'll keep doing this until it finds a few regions that it can look at, and then it'll start analyzing them for images. This saves us a lot of time rather than checking a billion boxes like you see on the first image. Once we use that, we'll put it through a softmax layer and for the candidate regions, and then using a normal everyday perceptron, we'll be able to know what images are inside each image. For our actual model, we used YOLO v5, which is an algorithm, you only look once, that actually takes a completely different approach. It divides an image by an S by S grid. Each cell is able to have its own bounding boxes and confidences. And what's really interesting is that it's able to make a class probability map, which will end up building confidence for final detections. And this happens super quickly, so it's really exciting to see how these models compare. We use the Ultra Analytics library for this model as well. So, analysis and metrics. As you can see, the baseline model seems like it's a lot more stable in learning in terms of all three metrics of recall, precision, and map. But the YOLO v5 model seems to perform very well towards the end of the epochs, meaning that we probably should have spent more time on the epochs. However, it took an absorbent amount of time to even get through these amount of epochs, around 2 to 3 hours each epoch. So as you can see through the map test metric, the YOLO v5 did much better than the baseline. So continued analysis, we thought this was very cool. If you look at the image on the right, you'll see that all of our guesses usually in prediction followed this green box in the center. And that's because we made the mistake of actually putting each of the image of the buildings usually around the center. So it would guess that much more frequently than not. But as you can see on the left, we do predict images correctly a lot of the time. What's very cool is that we can see the top of Wolf Ridge on the here with the 3 labels over there. And then you can see the 1 label on Fitzwillard and the 2nd label on Hunt Library, which is very cool to see at different angles. So what did we learn? Training time for object segmentation can take a very long time. it can take several dozens of hours to even get the computational time. And a lot of the times our computers can crash because it's a lot of data to take in. The type of photos for your computer vision project are the highest priority. I wish we took a lot more variety of images with several more angles. We also had a few iconic images that needed more noise, especially. Labeling is time consuming, and being able to generate more data would be very helpful. If we had a program to generate thousands of more images based off of the images we gave them, like a GAN, our time would be split tremendously, not having to label as many, and that would be perfect. Different models are also not black and white, so even though our YOLO model performed better than our baseline, you could see a lot more stability in the baseline. And perhaps if we gave it even more epochs, the baseline would perform even better. So there's a lot to learn about this, and we hope you enjoy this presentation. Thank you.